A huge thanks to Brian for sponsoring this video.
Good morning, fellow mathematicians. Welcome back to another video. Today, an exercise which I have exclusively reserved for the past few months to do in an improvised session here. And I think it's going to be quite the unique exercise. Here it is. Pause the video, read into it a tiny little bit. I also wrote it out here on the chalkboard. Now, why is this an interesting exercise to me? It's a coupled exercise. We begin with A, then we show something with B, and then we use the results of A and B to show that the cosine of 3 pi over 5 is equal to 1 minus square root of 5 over 4. This doesn't seem very significant at all, but this is an exercise which combines trigonometry and also algebra/analysis. The thing is, we are going to use a polynomial expression, or most certainly the roots of that thing, to derive ourselves a value for a trigonometric function, which is pretty unique, and you don't see that very often by solving a polynomial. And that's why I wanted to do it today. I think this is going to be a very brilliant exercise, just like the sponsors of today's video, brilliant. Check them out at the very end of the video. They are very cool. And I think this is going to be amazing. And I suppose that I can solve it here on camera in an improvised session. So the first part is that we need to show that x plus 1 is a factor of this polynomial right here. We can go two ways. We can either show that if we do polynomial division or something of that sort, that this right here is going to turn into a polynomial expression without a remainder. Or we can use, if x plus 1 is a factor of that polynomial right here, then that means that x plus 1 serves as a linear factor, so meaning negative 1 must be a root. Let us go both ways. For A, we are going to plug negative 1 into here, so we have 4 times, and this turns into negative 1, so negative 4, plus 2 times negative 1 squared, so plus 2, minus and minus becomes positive, plus 3 minus 1 is equal to 0. Hence, x plus 1 is a factor of this polynomial. I think this is called the factor theorem, if I'm not mistaken, in English. We have just shown that this right here is a linear factor. Or, as mentioned before, we could do polynomial division. This also does the job. So we are going to take x plus 1 and multiply it by a remainder polynomial, which we want to find out what it is, under the condition that it doesn't have a remainder, but if it divides it, then it doesn't have one. So the leading coefficient is 4. So for x squared, we also need something plus. We don't know the coefficient of the x term, plus ax, and then minus 1 overall to get ourselves the negative 1 here. Okay, if we multiply everything out, we get 4x cubed, so that does fit. Then plus ax squared minus x plus 4x squared. And then plus ax. And then minus 1. So this fits and this fits. So we just need to make those coefficients right here fit. 2 in front of the x squared. So we have a, and 4 must be equal to 2. So 4 plus a must be equal to 2. That means that a is equal to negative 2. Negative 2, so we get negative 2x, negative x, negative 3x, so that works out, meaning our remainder polynomial is equal to 4x squared, or the other linear factor. It's not linear yet, it's a quadratic factor, but you know what I mean, minus 2x minus 1. And this right here would be the other part. And if this right here is equal to 0, then that means that we get the other zeros of the function out. We can calculate this really quick. Dividing both sides by 4 gives us x squared minus 1/2 x, so minus 1/4 is equal to 0. That means the other two solutions, so one solution is negative 1. The other two, 2 and 3, are equal to 1/4 plus minus the square root of 1/16 plus a quarter. This right here is 4/16, so 5/16. So we get 1 plus minus the square root of 5/4. Oh. Yeah, and this was my sneaking suspicion. So we later need to show that the cosine right here is going to be one of the roots of this polynomial. So one of the roots of this polynomial, basically. Okay, but just one branch. We need to talk about the restrictions later. Okay. Now next up, express cosine of 3 phi through cosine of phi. Triple angle formula. I have no idea. But we could use addition formula at first, because 3 phi is the same as phi plus 2 phi. So let's go ahead and get started here. So cosine of phi plus 2 phi is going to be cosine and cosine. I am thinking through cosine of A plus I times the sine of A times, and then cosine of B plus I times the sine of B. So the multiplication there in the complex plane, cosine of phi times the cosine of 2 phi. And then we have I times sine times I times sine. So this is going to be negative. Yeah, it's the negative one. This is what I always need to think about. Cosine, cosine, and negative. Then we have sine of phi times the sine of 2 phi. And that's a bit better, because those are double angle formulas, and I know those at least. So this right here is the cosine squared of phi minus the sine squared of phi. And this right here is 2 times the cosine of phi times the sine of phi. Those are the double angle formulas. Okay. We want to express cosine of 3 phi just through cosine of phi, so we need to get rid of a bunch of stuff. Sine squared is the same as 1 minus cosine squared by the fundamental theorem of trigonometry. So this turns this into 2 times cosine squared minus 1. And this right here is 2 times cosine phi sine squared phi. Sine squared, as mentioned a second ago, is 1 minus the cosine squared. So all of this turns into 1 minus the cosine squared of phi. So what we got is we have 2 times cosine to the 3rd power of phi minus cosine of phi. And then we have minus positive, so plus 2 cosine cubed of phi. This turns into minus 2 cosine of phi. Okay, and this seems to be the triple angle formula. That is actually quite nice. I didn't know about that. I never really wrote an n-angle formula out for the cosine or the sine, but that's probably a nice induction exercise that you could use. Maybe I should look into that. So we have 4 times the cosine cubed of phi minus 3 times the cosine of phi. I hope that this is correct. Oh! Yes! That is gorgeous. Look at that. 4 times cosine cubed minus 3 cosine. So the only thing that's missing right now is 2 times cosine squared minus 1. That is the thing that is missing. I mean, point of the first exercise was to basically show that this one divides this, meaning we have found the root of this polynomial. So what we did is we set this equal to 0 and notice that -1 is a root and 1 plus minus square root of 5 over 4 is a root. Meaning the cosine of 3 pi over 5 is also a root of this polynomial here, since it's a root of this quadratic factor right here. That means if we were to plug cosine of 3 pi over 5 into here, we get 0 out. But we know that cosine of 3 pi over 5 is just so a cosine of 3 pi over 5 is basically equal to 4x cubed minus 3x. This is what we got right now, where x is cosine of phi. But by using this right here, we also know that 4x cubed minus 3x is the same as if we bring this to the other side, 1 minus 2x squared. Where x is cosine of phi. 1 minus 2x squared is 1 minus 2 times cosine squared of phi. Oh. That is at least this part right here. This is negative negative cosine of 2 phi. Oh, but I'm writing everything with respect to phi. We have phi being equal to... Why am I saying phi all the time? X is equal to, since this right here is 3 times pi over 5, then this is the cosine of pi over 5, right? So if we plug this in, we get negative the cosine of 2 times pi over 5. And this must be equal to the cosine to 3 pi over 5. And if this is the case, then we are basically done. Because then we have shown that this part is equal to this part, and hence it's the root of the polynomial, right? So if this right here turns into the negative cosine, if we take a look at this equality right here, then that means that we had a shift by pi. So if we have the cosine of 3 pi over 5 plus pi plus pi or minus pi, it really doesn't matter, right? So this is going to result in cosine of 8 pi over 5, but this is not the one we are looking for with a negative sign. So if we take negative, then 5 over 5, negative 2 pi over 5, but cosine is even, so we get rid of the negative here. But that's not equivalent, is it? So thing is, if we subtract pi, we don't have the same expression right here. We get 2 pi over 5, which is this part right here, which is 1 minus 2x squared overall. This is basically what we want to have. Oh, wait a minute. Is it the same? Am I tripping right now? I need to think for a second. If I take cosine value here, cosine of pi over 2 is the same as cosine of negative pi over 2. Those have the same value. Yeah, those are the same, right? If I'm not mistaken here, then that means that cosine of 3 pi over 5 is the same as 4x cubed minus 3x, where x is equal to cosine of pi over 5, which is the same as this thing right here. Meaning if we were to subtract this on both sides, we are going to get that 4x cubed minus 3x plus 2x squared minus 1 is equal to 0 overall, which is what we got right here, where our x is cosine of pi over 5. And if we plug cosine of pi over 5 into here, this right here is the same expression for both of this, then we get out that cosine of 3 pi over 5 is equal to 1 minus square root of 5 over 4. Am I dripping, bros? Am I dripping? I think this works. Oh. Can we call this QED? I'm not certain right now, actually. Maybe I should put some annotations here to further clarify if what I did right here was right. I need to try it out a tiny little bit more on paper, but for now it does make sense, at least in my book. Yeah, I think we can call it quits right here. I don't know how to put it into a nice notation-wise thing right now. So I'm going to put a little annotation here because I'm not 100% certain if my reasoning was 100% complete. Hey there, Jens from the 4-minute later future. I just recorded my sponsored message and I was thinking my arguments were quite lacking because our polynomial has 2 more roots, plus and minus. And the only thing that we know right now is that the cosine of pi over 5 is a root to this polynomial. This is what we found out here because if we plug it into this equation right here, we get 0 out because of everything that we did here algebraically. Cosine of pi over 5 is less than the cosine of pi over 2, obviously. So it must be a positive value. It's somewhere here. So it can't be 1 or no, negative 1. It can be negative 1. Obviously 1 minus square root of 5 is less than 0. So this doesn't work. So since it's a root, we have that cosine of pi over 5 must be equal to 1 plus square root of 5 over 4. And now that we got that, we can try to actually show that the cosine of 3 pi over 5 is equal to the other root, because it's actually not obvious, and this is why I was still pondering there, because it wasn't obvious to me either. But we know that the cosine of 3 pi over 5 is the same as this thing right here. So 1 minus 2 times cosine squared of pi over 5. Okay. And now we can go ahead and maybe compute it a bit more. Now, cosine of pi over 5 is 1 plus square root of 5 over 4. So by plugging this in, we are going to get 1 minus 2 times 1 plus square root of 5 over 4, but squared. This is 1 minus, this turns into 1, no, this is 16 down here, so over 8 something. Then we take this squared, 1 plus 2 square root of 5 plus 5. This right here is 1, so 8 over 8. This is something over 8. This is negative 3. 8 minus 3 is 5. No, 1 plus 5 is 6. 8 minus 6 is 2. Minus 2 times square root of 5. And taking the 2 out gives us 1 minus the square root of 5 over 4. And this is the cosine of 3 pi over 5. Oh, nice. Yeah, this is better, I suppose. Yeah, now we have fully used it. And now the chain of thought is completed. That wasn't a satisfying end to the improvisation, the initial end, because I still wasn't sure if everything was right. But I didn't want to stand here and ponder for 30 more minutes. Yeah, that's cool, I suppose. Thank you for watching. Have a great one. See ya. But I think this should do the trick. We have used both things right here, triple angle formula, to turn this into a polynomial. We have found out what the roots of the polynomial are at the very beginning. And if we were to plug this in, then we should get the desired result out, I suppose. Yeah, I think this does it. And if you wish to see more trigonometry, algebra, calculus, and more of the mathematics that we did today, then the contents of today's sponsor Brilliant might be the perfect fit for you. Now, if you are still on the lookout for a great online source to learn something new on a daily basis, either at home or on the go, then Brilliant might be the perfect fit for you. With their nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, physics, computer sciences, chemistry. Really doesn't matter what you want to learn in the STEM field, Brilliant is there to serve you the finest, the thickest STEM meat of them all. Their course concept is quite simple. Do it interactively, with a lot of visuals and graphically that you can play around with to learn something quite quickly that you would otherwise, for example at university or at your regular school, take months to understand. With Brilliant, you can lay the groundwork for a lot of things in STEM by using their interactive courses. As mentioned previously, it's all about grabbing something with your own two hands, grab the mouse, play around with this graphic over here or this parabola over there. Really doesn't matter. Point is, they don't want to bombard you with all this abstract stuff at first. They want you to slide into the topics very, very intuitively. And this is their strongest feat that they can provide the STEM community with online with their courses. Doing stuff visually. If you are a visual learner, Brilliant is the perfect place for you to start learning something new today. By using my link down there at the top of the description, brilliant.org/flammable maths, or the QR code somewhere up here in the corner. Try the whole landscape of Brilliant for completely free. And if this feels like this could turn into a long-term relationship between you and their services, then make sure to use my link in its entirety. and get 20% off an annual premium subscription. It's seriously worth it. You can learn so much new stuff over there in a matter of just hours. It's way more accessible than anything you can find physically in a classroom, for example. Just give it a shot, try it out. It's amazing. This is why I love having Brilliant here as a sponsor, because they really provide the STEM community with a huge service. Try it out and support the channel this way. And I thank you guys for watching. And I think I found an idea for justifying what I said at the very end a bit better. I'm gonna make a tiny little edit and put it at the very end before the sponsor message. But up until the next video, I wish you guys a flammable day. See ya!